Atoms can give off light. Now, this isn't just hydrogen. Any atom can give off light. But in order to do so, they must first receive energy and become excited. The energy that is absorbed will equal the amount of energy that is released when that atom returns to what's called its ground state. And as that energy is released, that atom will emit light. The photon, the color of the photon, corresponds to the amount of energy. So red light is lower energy, blue light, purple light are higher energy. Atoms exist in either a ground state or an excited state. The ground state is the atom in the lowest possible energy state. And then if atoms absorb energy, they will go up into an excited state. But they cannot stay up in that excited state. They have to return to their ground state. And so to return to their ground state, they release energy. We see that energy in the form of light. So we say they are releasing photons of light. And again, the color of the photon is going to correspond to the amount of energy. This is just a joke, because burgers are in the ground state, and ground state is low with energy. So the energy in the photon exactly equals the amount of energy absorbed by the electron to get to the excited state. We know energy released has to equal energy absorbed. So that way we can actually calculate how much energy was absorbed by using the energy of the photon that was emitted. So an atomic emission spectrum is a set of frequencies of electromagnetic waves emitted by atoms of an element. Basically, it is colors, because that's what we're talking about here. The electromagnetic waves are in the visible spectrum, at least the ones we can see, right? So every atom releases a unique, that's important, set of frequencies of waves, a unique set of colors. If I were to look at white light through a prism, it's going to split into a rainbow, right? With these, what you do is you put a gas into a tube, you run electricity through it to charge it up, and then you view the light that is released through a prism. And instead of being a rainbow, you're going to get separate, distinct lines of color. And each line of color corresponds to a photon with a specific amount of energy. So this is kind of the setup for seeing an emission spectrum. You have your gas discharge tube, you're running electricity through it, you view that light through a prism, and it always, every sample of hydrogen splits into these 4 unique spectral lines with those exact wavelengths. Those are wavelengths, 410 nanometers, 434 nanometers, etc. So every single time it splits the exact same way, which is interesting. And it's also interesting that it's not a rainbow. It's just these 4 lines of color. Every element has a unique set of lines, and it's not always 4. Sometimes it's more, sometimes it's less. So these set of lines, these exact lines, are unique for every element. This one happens to be hydrogen. Only certain types of photons are produced when hydrogen atoms release energy. So that's where we're getting these certain distinct colors. The reason for that is because the energy in the hydrogen atom is quantized. And a hydrogen atom and other atoms contain discrete energy levels. What we mean by discrete is that it's either on one energy level or it's on another energy level. It's never in between. And so the electrons get excited. They go to a higher energy level. And then as they fall back down, they release those colors of light. Using hydrogen's emission spectrum, Bohr developed a model of the atom that has quantized energy levels. So the energy levels are quantized, the space between them is specific, and an electron has to absorb that specific amount of energy to be able to move to the next energy level. He thought electrons moved in a circular orbit. We now know that that is not the case. He also thought that electrons would jump between levels by absorbing or emitting photons of a particular wavelength. This is true. So if I have an electron here on the first energy level, it can absorb energy and move up, but it can't stay up there. It has to eventually go back to its ground state, and when it does, it releases energy, the same amount of energy that it absorbed, and we see that energy as light. The Bohr model, it turns out, is incorrect. Since he used hydrogen's emission spectrum to develop it, it turns out it only applies to hydrogen. We also, of course, know that electrons do not move in orbits. So what do they do? We started this chapter with the dual nature of light, and we had to start with the dual nature of light because that is what de Broglie used to propose our current model of the atom, which is called the wave mechanical model or the quantum mechanical model. So light, which is energy, has particle characteristics. And that was a widely accepted fact that had been supported by a lot of experimental evidence. So if light, which is energy, can have particle characteristics, maybe a very, 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 very small particle like an electron could have wave characteristics. And so de Broglie treated electrons like waves. And Schrodinger put together an equation treating electrons like waves to kind of see what kind of model for the atom that would give them. So it turns out electrons do not follow distinct orbits like planets orbiting the sun, but they exist in something called an orbital. It's different, even though it sounds the same. An orbital is a region where there's a high probability of finding the electron. It's about 90% probability. Even though it looks like there is in this picture, this is a picture, obviously there's boundaries of a picture, there is no distinct boundary of an orbital. Just the further out you get, the more the probability goes down, but there's no like end to an orbital. We never know exactly where an electron is. We only know where it probably is, where it might be. Heisenberg developed the Heisenberg uncertainty principle, which basically says that it's impossible to know the exact position of an electron at any time. And this is because as we see electrons, that actually changes their path. This is another little joke. So the way you see things is that light bounces off of it. And obviously light bouncing off of you isn't going to move you around because you're big enough. But electrons are very, 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 very small. And so if an electron was originally on this arc path here, when light comes in and hits it, it's so small that that little photon of light actually pushes it off into a new path. And so we can say, yes, this is where the electron was. I see it where it was. But as soon as we see it, it moves on to a new path. So this whole quantum mechanical model is all about probability of finding an electron in a particular place. So orbitals do not have sharp boundaries or an exactly defined size. They do contain 90% of the total electron probability, which means 10% of the time, it's somewhere else. Atoms have discrete energy levels. We know this from the emission spectrums. They are called principal energy levels. They are labeled N. So N equals 1 is energy level 1, N equals 2 is energy level 2, etc. The higher the number, the farther away from the nucleus the energy level is. So energy level 1 is closest to the nucleus, and then 2, 3, 4, 5, 6, 7 get further and further away. Within each energy level, there are sublevels. The sublevels are labeled with letters S, P, D, and F. In energy level 1, there is one sublevel, an S sublevel. In energy level 2, there is an S and a P. Energy level 3 has S, P, D, and then energy level 4 has S, P, D, and F. And everything above 4 has all 4 sublevels. The letters of the sublevels correspond to their shapes, but I don't worry about shapes really too much. So within the sublevels are the orbitals. So it goes energy level, and then within the energy levels are your sublevels, and then within the sublevels are the orbitals. And remember, the orbitals are the areas of probability of finding the electron. Each type of sublevel has a different number and shape of orbitals, and 2 electrons can fit into each orbital. So the S sublevel has 1 orbital, the P has 3, D has 5, F has 7. This is a very important slide when we get to electron configurations. Each orbital can be filled with 2 electrons, half filled with 1 electron, or empty with 0 electrons. So just because the P sublevel has 3 orbitals, that doesn't mean it's all full up. It could have just 1 electron in that entire sublevel, or 0 electrons in that entire sublevel. So S is a sphere, P is kind of a peanut shell, D is kind of a clover leaf, and then F shapes vary. So that's what these are. This is the S, P, D, and F. And so this is orbital 1, orbital 2, orbital 3 of P, orbital 1, 2, 3, 4, 5 of D, etc. That's why there's multiple of P, D, and F. But again, don't worry about the shapes too much. So energy level 1 is closest to the nucleus. It has one sublevel in S. It has one orbital, the 1s orbital. So orbitals, energy levels are given a number. The sublevels are given a letter. And then the orbital is the number plus the letter. It's kind of the address of you, if you will, of the electrons. Like your address has a number and a street, right? So it's kind of the same thing. Energy level 2 has 2 sublevels, an S and a P. It has 4 orbitals. Don't worry about the X, Y, and Z. That just has to do with what plane it's on. So it has the 2S and then 3 2P orbitals. So there's 4 total. Energy level 3 has 3 sublevels, S, P, and D. So it has 9 orbitals, the 3s orbital, 3 3p orbitals, and 5 3d orbitals. And then energy level 4 has 4 sublevels, S, P, D, and F. It has 16 orbitals. Everything above energy level 4 also has 16 orbitals because they have all 4 sublevels. So if we said that the building of Catholic Central was an atom and you were an electron, we can find your place in the building just like we can find the place of an electron in an atom. So the floor that you are on corresponds to your energy level. Are you on the first floor or the second floor? Within the second floor, there are many different classrooms, and so that corresponds to the sublevel. And then within the classroom, there's different places you can be, the desks, and so that's the orbitals. But you're not, even during class, you're not in your desk 100% of the time, right? You might get up to sharpen a pencil, or you got to go ask your friend a question real quick. So about 90% of the time, you're in the desk. Same thing with the electrons. Electrons can move in between desks, or I should say you can move in between desks in a classroom. So electrons, same thing, can move in between orbitals in a sublevel. When class is over, you go to a new classrooms. You're not stuck in this sublevel. So same thing with electrons. They can move between sublevels. They can move between energy levels, just like you can move from the first floor to the second floor. So we are going to do ground state electron configurations. And that's where the electrons are in the ground state, in the lowest energy state. But it's important for you to understand that that's not 100% of the time where they are, that those electrons can move, especially if they are excited.